This is a video from section 1.4 in a linear algebra class. Let's look at the following theorem. The matrix A, which is equal to the matrix ABCD, is invertible if and only if AD minus BC does not equal 0. And the inverse is given by 1 over AD minus BC times the matrix D negative B negative CA. Okay. Now, for example, if I let A equal the matrix 3, 4, 5, 6, and I want to know, is A invertible? Well, if I take 3 times 6, and then I subtract 5 times 4, I get 18 minus 20, which is equal to negative 2, and that doesn't equal 0. So, by the previous theorem, A is invertible. And on top of that, we can actually find its inverse. And so A inverse is equal to 1 over, again, it's 3 times 6 minus 5 times 4, which I already showed was negative 2. So A inverse is 1 over negative 2 times. Now, how I come up with the matrix is this. I take the entries along the main diagonal and swap them. So I'm going to put the 6 in the upper left corner and the 3 in the lower right corner. And then I change the signs of the entries along the other diagonal. So here I put negative 4, and here I put negative 5. Now, I can take every entry and multiply by half. When I do that, the first row is 3, negative 2. Half of 6 is 3. Half of negative 4 is negative 2. That's the first row. In the second row, we get negative 5 over 2, 3 halves. And I claim that's the inverse of 3, 4, 5, 6, that matrix. Okay, now, let's put this theorem to use. Suppose I ask you to find a unique solution to the given linear system. Now, here's the system. 2x minus 2y equals 4. And x plus 4y equals 4 as well. Now, I want to write this system in matrix form. Now, I'm going to take the coefficient matrix. So, in other words, I'm going to form a matrix by peeling off the coefficients of each of the variables. So, in the first row, I get 2, negative 2. In the second row, I get 1, 4. So, again, that's my coefficient matrix. I'm going to multiply by the column vector xy. And I'm going to set this equal to 4, 4, like so. Okay. Now, my A is the matrix 2, negative 2, 1, 4. If I take 2 times 4, and I subtract off negative 2 times 1, that's 10, which doesn't equal 0. And so what that tells me is A is invertible. by the previous theorem. Now, the question is, what is A inverse? A inverse is, so I'm going to take 1/10, okay, that 10 is AD minus BC. Now, again, this is how I think of the matrix. I'm going to take the entries along the main diagonal and swap them. So I'm going to put a 4 up here and a 2 down here. And then I'm going to take the entries along the other diagonal and change the sign. So I'm going to put a 2 up here and a -1 down there. Okay. Now, when I go to simplify that, I get 2/5, 1/5, -1/10, 1/5. Now, we're almost there. So I'm going to take 2, -2, 1, 4. And I'm going to multiply by the column vector xy. And I'm going to leave a little space, and I'm going to set it equal to 4, 4. So this is what I do. I'm going to multiply both sides on the left by A inverse. When I do that, I'm going to isolate the column vector xy. Okay? So let's do this again. I'm going to multiply on the left by 2/5, the matrix, 2/5, 1/5, -1/10, 1/5. Okay? So I'm multiplying on the left by that matrix. And if I do it to the left, I got to do it to the right. So I'm going to multiply by 2/5, the matrix, 2/5, 1/5, -1/10, 1/5. Just like this. Now, on the right side, so think of this as the dot product. I'm going to take 2/5 times 4, and then I'm going to take 1/5 times 4 and add them. When I do that, I get, well, let's see, I get 8/5 plus 4/5 is 12/5. Then I'm going to take -1/10 times 4 and 1/5 times 4 and add them. And so when I do that, I get -2/5 plus 4/5, which is 2/5. That goes there. That's the right side. Now, on the left side, because I really want to make sure you guys follow, I'm going to use the associative property, and I'm going to get 2/5, 1/5, -1/10, 1/5 times 2, -2, 1, 4. And I'm going to take that times the column vector xy. Now, if all went well, if I take these two matrices and multiply them, I should get the identity matrix. And the identity matrix is given by 1, 0, 0, 1. So I get the matrix 1, 0, 0, 1 times xy equals, on the right side, we get 12/5, 2/5. Let's write that again. 12/5, 2/5. But if I take the identity matrix times xy, we get the column vector xy. And then we get 12/5, 2/5 on the other side. And so reading this off directly, we get x equals 12/5, y equals 2/5. Now, it doesn't hurt to check, right? Now, this is our system. 2x minus 2y equals 4. And then we have x plus 4y equals 4. If I replace x with 12/5 and y with 2/5, I get 2 times 12/5 minus 2 times 2/5. And does that equal to 4? Well, I'd say the answer is yes. And then if I take 12/5 plus 2 times 2/5, does that equal 4? The answer is yes, right? Absolutely. Oh, excuse me, not yet. This should say 4 times 2/5. Now, does that equal 4? And the answer is yes, absolutely, because 12 plus 8 is 20. 20 divided by 5 is 4. So this would be the correct solution to that system. It's a good question. And it's a linear algebra approach to solving that type of problem. And we have a theorem. If A and B are invertible matrices, with the same size, then it turns out AB is invertible. And the inverse of A times B is B inverse A inverse. Now, so proof. Let's look at why this works. Now, we know the inverse of a matrix is unique. There's only one inverse, in other words, okay? So we will first show that if I take AB and multiply it by B inverse A inverse, I get I back. And if I take B inverse A inverse and multiply by AB, I also get I back. So let's go for this. If I take AB and I multiply by B inverse A inverse, by the associative property, this is A times B inverse A inverse. But this is equal to AI A inverse, right? But this is A inverse, which is equal to I. So that's the first part. So therefore, if I take AB times B inverse A inverse, I get I back. Now, if I take B inverse A inverse and multiply by AB, this is B inverse times A inverse A times B, which is B inverse times I times B, right? But when you multiply by the identity, you just get the actual original matrix back. So you're going to get B inverse B, which is equal to I. Therefore, B inverse A inverse times AB is also I. Now, what this shows B inverse A inverse is the inverse of AB. Therefore, AB is invertible. And we can represent the inverse of AB by, and then in parentheses, I'm going to put AB and then inverse. So it's the inverse of A times B. That's how we can represent the inverse. And since the inverse of any matrix is unique, then the inverse of A times B is B inverse A inverse. And now, let's go over an example of this, and then we'll call it good for this video. For example, suppose I ask you to simplify, and I'm going to have the inverse of A times B times AC inverse times D inverse C inverse inverse, right? D inverse. Now, let's start here. So I'm going to take the inverse of A times B. I'm going to multiply by AC inverse times the inverse of D inverse C inverse, D inverse. Now, if I apply the properties, right, this is B inverse A inverse times AC inverse times. Now, I'm going to get C inverse inverse times D inverse inverse. Or another way you could say it is the inverse of C inverse times the inverse of D inverse. D inverse. It's real slick, because watch what happens. So this is B inverse A inverse times AC inverse times CD D inverse. And then it just turns into a regrouping exercise. So this is B inverse times A inverse A, C, well, we can even do better, because then you do A inverse A, so I'm grouping these, right? Is that okay? I'm grouping these, and I'm going to group these. And so, in other words, I'm going to multiply by C inverse C times D inverse. So I group these together as well. So it's all the associative property. So this is B inverse times I times I times I. But this is equal to B inverse. And that's how you simplify the example from the notes. Okay, that'll do it for this video. We looked at the inverse of a 2x2 matrix, a special case, and we solved a system applying that theorem. We solved a system of two equations with two unknowns, applying the inverse of a matrix. We looked at the inverse of a product of two matrices, and then we did an example where we applied that theorem. So again, this was a whole presentation on invertible matrices. Thank you.